Hello everyone and welcome to our new topic, asymptotic analysis. So in this section, we will dive into the concept of asymptotic analysis and explore the powerful tool of asymptotic notations which help us analyze the efficiency of algorithms. So, efficiency of an algorithm is all about how well it utilizes resources like time and storage. So, as you might have noticed, the performance of an algorithm can vary with different types of inputs. As the size of the input increases, the algorithm's performance might change significantly. So, the study of how an algorithm's performance changes with the increase in the size of the input is what we call asymptotic analysis. So, it allows us to understand how an algorithm behaves as the input becomes extremely large, and it is a fundamental concept in analysis of algorithms. Asymptotic notations are the mathematical tools we use to describe the running time of an algorithm as the input approaches a particular value or a limiting value. In simple terms, they help us understand how the running time of an algorithm changes with the size of its input. So consider the example of bubble sort. When the input array is already sorted, the algorithm takes linear time, which is the best case scenario. However, when the input array is in reverse order, it takes quadratic time, which is the worst case scenario. And when the input array is neither sorted nor in reverse order, it takes an average amount of time. So these different scenarios are captured and denoted using asymptotic notations. There are three main asymptotic notations we will explore in this section. First one is big O notation. It represents the upper bound of the running time of an algorithm. It gives us the worst case complexity of an algorithm. So next we have omega notation. It represents the lower bound of the running time of an algorithm. So which means it provides us with the best case complexity of an algorithm. So at last we have theta notation. This notation encloses the function from above and below, and it represents both the upper and lower bounds of the running time, making it suitable for analyzing the average case complexity of an algorithm. So let's take a closer look at each of these asymptotic notations and understand their significance. The big O notation. Big O notation gives us an upper bound on the running time of an algorithm. It tells us that the algorithm's performance won't exceed a certain level, even for larger inputs. This makes it highly useful for analyzing the worst case scenario of an algorithm. The above expression can be described as a function f of n belongs to the set big O of g of n if there exists a positive constant c such that it lies between 0 and cg of n for sufficiently large n. For any value of n, the running time of an algorithm does not cross the time provided by big O of g of n. So since it gives the worst case running time of an algorithm, it is widely used to analyze an algorithm as we are always interested in the worst case scenario. The omega notation. Omega notation provides a lower bound on the running time of an algorithm. It assures us that the algorithm will perform at least as well as the specified bound, even for larger inputs. Omega notation is handy for analyzing the best case scenario of an algorithm. The above expression can be described as a function f of n belongs to the set omega of g of n if there exists a positive constant c such that it lies above c of g of n for sufficiently large n. So for any value of n, the minimum time required by the algorithm is given by omega of g of n. The theta notation. Theta notation is like a sandwich. So it encloses the function from above as well as below. It represents both the upper and lower bounds of the running time. As a result, it is perfect for analyzing the average case complexity of an algorithm when the performance can vary depending on the input. The above expression can be described as a function f of n belongs to the set theta of g of n if there exist positive constants c1 and c2 such that it can be sandwiched between c1g of n and c2g of n for sufficiently large n. If a function f of n lies anywhere in between c1g of n and c2g of n for all n which is greater than n 0, then f of n is said to be asymptotically tau bound.